Complete PLC programming course from zero to industrial level. Prepared by engineer Adil Saleh. Industrial Network Architecture. Let's begin our overview of how modern industrial automation networks are structured. Modern factories do not rely on flat, disorganized networks to function. A single production line contains thousands of moving parts, and routing all of that data into a single chaotic pool would lead to immediate system failure. To achieve reliable automation, raw machinery must be managed through a strict, layered logic architecture. This vertical four-tier model starts with sensors and actuators. Next are PLCs, then SCADA systems, and cloud systems at the top. This purposefully isolates localized high-speed machine control from macro-level data analytics. Each level communicates dynamically with the layers above and below it. However, this communication follows a strict chain of command. A layer only exchanges data directly with the layer immediately adjacent to it. A sensor never talks directly to the cloud. By enforcing this rigid hierarchy, facilities prevent massive industrial systems from collapsing under the weight of their own data. Let's look at the absolute lowest tier of the industrial hierarchy, the physical foundation. Here, sensors are deployed directly on the machinery. Their specific role is to collect continuous, raw data from the physical environment, converting properties like heat or motion into digital pulses. Alongside them are actuators, which are the mechanical components, like valves and motors, responsible for executing physical movements. The strict limitation of this lowest level is that it is purely reactive. A sensor can detect a temperature spike, but it possesses no independent intelligence or decision-making power. The binary data generated here remains entirely useless without a processing mechanism to intercept and interpret it. Level 1 acts strictly as the nervous system's nerve endings, sensing the physical world, but requiring a brain to dictate the reaction. That brings us to the second level, the processing brain, governed by the PLC, or Programmable Logic Controller. PLCs ingest the raw data streams from the sensors below. To process this, the PLC relies on step-by-step coding logic. If sensor A equals high, following strict indentation rules, the PLC evaluates this. Once the equation is met, the code reaches the then statement. The output phase initiates, sending an immediate control command back down to the actuators to open a valve. The critical feature of this loop is speed. PLC control happens in real time, frequently executing these logical equations in a matter of microseconds. The PLC does not need to ask for permission from higher levels to execute these immediate safety and operational functions. By managing this logic locally, PLCs grant the factory floor the autonomy to operate massive machinery safely and continuously in real time. As we step up to the third level, we shift focus from localized machine control to macro-level facility oversight. This is the SCADA layer. While a single PLC has a narrow focus, the SCADA system provides a broad, facility-wide view, aggregating multiple real-time data streams. SCADA's primary function is to aggregate the data from hundreds of individual PLCs and present it within a unified monitoring interface. Through this interface, operators can monitor entire production processes, track critical alarms, and adjust operational parameters without ever physically visiting the machines. SCADA monitors and supervises, but it does not directly drive the motors. It relies entirely on the PLCs below to execute the actual physical adjustments on the factory floor. By pulling these individual data streams together, SCADA translates raw machine operations into a cohesive, centralized narrative of the factory's current health. Finally, we ascend to the absolute top of the architecture, the cloud systems layer. While SCADA handles the immediate status right now, the cloud handles historical data, storing massive amounts of information over months and years. Its core function is to perform deep data analysis and identify long-term optimization trends. Once the cloud calculates an optimization, it sends the new operational parameters back down the chain, adjusting the SCADA setpoints, which then seamlessly update the PLC logic below. This top-down communication ensures an entire facility can adapt continuously to new efficiency targets without requiring engineers to manually reprogram every individual machine. The cloud tier elevates factory management from basic physical automation into strategic, predictive intelligence. Look at the completed structure. This exact configuration is known as the industrial automation hierarchy. It guarantees 3 specific capabilities. First, real-time control, handled entirely by the PLCs. Second, centralized monitoring, provided by the SCADA systems. Third, global data analysis and long-term optimization, executed by the cloud. This strict division of labor ensures that heavy data processing in the cloud never interrupts the microsecond safety controls required on the factory floor. This 4-layer architecture is the bedrock foundation of all Industry 4.0 systems. Mastering this specific flow of information, from discrete sensor inputs to complex cloud analytics, is what separates basic engineering from true industrial-level proficiency. By adhering to this step-by-step logic, we build networks that are robust, secure, and capable of operating continuously at an